Here is our second practice problem based on naming of compounds from the section Organic Chemistry. Here we've got a question 2 that says letters A to H in the table below represent 8 organic compounds of different homologous series. Now, I mentioned to you guys in the previous video that we always start off by analyzing our table. Analyze each compound, all of these letters, understand which homologous series it belongs to, what its functional group is, because when you do that beforehand, you kind of already answer most of the questions in doing so. Okay, so if we look at A, we've got C9H18. Now, firstly, what we know about A is that it is a hydrocarbon because it contains only carbon and hydrogen. So it is either going to be an alkane, alkene, or alkyne. However, when we look at the subscript, so we've got the 9 and the 18, there are 9 carbons and there are 18 hydrogens. Think of the general formulas that you learned. This has the format CnH2n. So A is definitely an alkene. Okay, just because of the format CnH2n, which we have, the general format, or the general formula. Then if we look at B, we've got pentenyl. So the prefix Al tells you this is definitely an aldehyde. Now, going on to C, we've got CH3CHOH. So the fact that you've got the OH here, that tells you that this is an alcohol. Remember, functional group of an alcohol is the OH, which is the hydrosyl group. Now, when we look at compound D, we notice that we've got only carbons and hydrogens, so it's definitely a hydrocarbon, either alkane, alkene, or alkyne. But based on the carbons and what is around them, we notice that we've got this one carbon alone, meaning that it will be bonded to the carbon before it and the carbon after it, but that is only 2 bonds, which means that there's 2 other bonds missing. Here we are expecting to have a triple bond. Now, when it comes to alkenes and alkynes and you are given condensed structural formula like this, sometimes it's a bit difficult for you to just look at it and know what it is. But if you draw out the structural formula, so you're able to visualize what's happening, it's easier for you to see what the functional group is. So here, D is going to be an alkyne. So we are expecting to have a triple bond on the second carbon. Now, going on to E, we notice that we've got a carbon with a double bond oxygen and single bond oxygen. There are other carbons on either side. So based on what we see here, this is definitely an ester. Looking at compound F, we notice that there is a carbon with a double bond oxygen on it, and there's carbons on either side. So this has to be a ketone. Now, compound G, we immediately notice that we've got 3 bromines. They are halogens. This is definitely a haloalkane. And H has the carbon with the double bond oxygen, single bond OH. It is on the first carbon from the right. So H is definitely a carboxylic acid. Now that we understand and we know the homologous series and the functional group of each compound A to H, we're now ready to answer the questions. 2.1 says, define the term homologous series. Okay, so here's the first definition. There's actually 2 different ones that are used. The first one is a series of organic compounds that can be described by the same general formula. And the second one would be a series of organic compounds in which one member differs from the next with a CH2 group. But this seems to be the more commonly used definition. Now, 2.2 says write down the letter or letters for And the first one they want is a ketone. Now, we had already identified a ketone from our table. That was compound F. 2.2.2 says two compounds that are functional isomers of each other. So let us just remind ourselves what functional isomers are. They are organic compounds with the same molecular formula but different functional group. Now, you guys have learned part of your syllabus that there are only two functional isomers that we work with. The first one is ketones and aldehydes. And the second one is carboxylic acids and esters. Now, we actually had all four of these, but we need to refer to our diagram to see which ones it's going to be. Now, I just want to show you why it won't be the aldehyde and the ketone. The reason is because our aldehyde is pentenyl. There's 5 carbons in the parent. And if we look at the ketone, it also has 5 carbons in the parent, but it has this extra branch, which the aldehyde does not have. Okay, so in total, the ketone here has 6 carbons in total, but the aldehyde that we're working with only has 5. So it's not going to be those two. Because remember, they have to have the same molecular formula, meaning that the number of carbons, the number of hydrogens, the number of oxygens needs to be the same for both of the compounds. Now let's look at our ester and our carboxylic acid. The ester has 1, 2, 3, 4 carbons, and the carboxylic acid also has 1, 2, 3, 4 carbons. So the answer should be E and H. Notice how, if we had to write down the molecular formula, it would be exactly the same. But they have different functional groups. So they are known as functional isomers. That is E and H. 2.2.3, we need a compound with a general formula CnH2n-2. That is the general formula for an alkyne. We have identified an alkyne above. Alkyne was D. So the answer for 2.2.3 is D. For 2.2.4, they want a compound containing a carboxyl group. A carboxylic acid contains a carboxyl group, so that is going to be H. Now 2.3 says, give the structural formula of a positional isomer of compound C. So let's have a look at compound C, and we need a positional isomer. Now, to understand what a positional isomer is, they are organic compounds that have the same molecular formula but different position of the functional group. From this condensed structural formula, we see that the OH on this alcohol lies on the second carbon. All we have to do is take that OH and put it on a different carbon. So let's start off by drawing this out. So the compound has 4 carbons in it, right? So the parent chain has 4 carbons. And the compound that was given to us had the OH on the second carbon. We just need to take that OH and move it onto a different carbon. Now I know some of you may be thinking, okay, it's on the second carbon, let's move it onto the third. That would be wrong. The reason why is, say for example, you put the OH on this carbon which you think is the third carbon. This is actually not the third carbon. This is still the second carbon. It's just that now it's the second carbon from the right. So please beware of mirrored compounds. Mirrored compounds means that when we count from the left and when we count from the right, we get the same number. So putting it on the second carbon from the right, which you may think is the third carbon, would actually be wrong because your compound stays the same. Instead, we need to have this on the first carbon. It could either be the first carbon on the left or the first carbon on the right. Either way, whether you put it on the first from the left or the first from the right, it is still on the first carbon. So it does not matter. I'm just going to put it on the first carbon from the left. Now we can fill in the hydrogens on our remaining bonds. So there we have it. This is the structural formula of a positional isomer of that compound. And also, sorry, this was 2.3, not 2.4. Okay, let's have a look at 2.4. It says, write down the IUPAC name of So starting off, we need IUPAC name for compound F. Okay, so let's just erase the current information we have on it. Now your first step when writing down your IUPAC name is to find the longest parent chain. So if we go left to right, we have 1, 2, 3, 4, 5. If we go right to left, we have 1, 2, 3, 4, 1, 2, 3, 4, 5. So either way, 5 is the longest parent chain. So I'm going to take 5 straight across. So that's what I have. Then I noticed that there is this carbon that is sticking out. That is definitely a branch. So this carbon, it's only one carbon with 3 hydrogen. We know that is going to be methyl. And going back to our parent chain, we need to number these carbons so that the functional group lies on the lowest carbon. Now remember here, your functional group was this double bond OH because it was a ketone. If you number left to right, you'll have 1, 2, 3, 4. Your functional group will be on the 4th carbon. But if you number right to left, you'll have 1, 2. Your functional group will be on the 2nd carbon. So here, it is better for us to number right to left. Now, doing so, what we notice is that our functional group now lies on the 2nd carbon and our methyl branch lies on the 3rd carbon. So let's name this. This is going to be 3-methyl pentan-2-one. Okay, so there we go, 3-methyl pentan-2-one. So the 3 indicates the carbon that the methyl is on, and the 2 in between the parent chain indicates the position of the functional group. So that double bond oxygen was on the 2nd carbon. Now for 2.4.2, we need the IUPAC name of compound G. So let's go up to compound G. Just going to erase all of this that we have here. Now the first step would be to identify the longest parent chain. And remember that your parent chain has to have all the carbons that got the BRs on them, that have the bromos on them. Okay, so I'm going to go left to right. I'll have 1, 2, 3. You see, you cannot count straight. You can't say 1, 2, 3, 4, 5 because you're going to leave out a carbon at the bottom that has a BR on it. So that would be wrong. So we're going to count 1, 2, 3, 4, 5, 6. That is our longest parent chain. We've got these 6 carbons. Now, before I number them, I just want to identify the branches. So here's our branches. We've got 3 bromos. So we know that's going to be tri-bromo. And we've got these 2 carbons sticking out here. So we know the name of that is going to be ethyl. Now, when it comes to numbering your carbons, this is a haloalkane. So when you number your carbons, give precedence to the halogen because remember your halogen is your functional group. So if we count left to right, we'll have 1, 2. Notice that your first halogens are on the 2nd carbon. But if you number right to left, you have 1, 2, 3. Your first halogen will be on the 3rd carbon. Since we need the lower carbon, we're going to go left to right. So we've got 1, 2, 3, 4, 5, 6. And what we notice here is that on the 2nd carbon, we have 2 bromines. On the 4th carbon, we have 1 bromine. And on the 3rd carbon, we have an ethyl. Please, please, please remember that when it comes to naming your branches, you always name your branches alphabetically. Even though there's 3 bromines and it's going to be tri-bromo, we ignore the tri part. We still look at it as if it starts with a B because it's for bromo. So alphabetically, bromo goes first and then ethyl. Please do not think that because now it's tri-bromo that T comes after E. We don't worry about the prefixes. We worry about the branch name itself. So bromo starts with B. So we're going to mention the bromos first. But we need to mention the position of all three of them. So we've got 2 bromos on the second carbon and 1 on the fourth carbon. So that is going to be 2, 2, 4 dash tri-bromo. Now before you put the name of a new branch, you have to put another dash. And then we had the ethyl. So let's just scroll up to see where the ethyl was. It was on the third carbon. So that's going to be dash 3 dash ethyl. And the parent chain here had 6 carbons. So this is going to be hexane. So that is its IUPAC name. Now for 2.5, we want the structural formula of compound B. We go up to compound B, it was pentanol, so that is an aldehyde. Aldehyde with 5 carbons because it's pent. So let's draw our 5 carbons. Remember, for an aldehyde, your functional group is always on the first carbon. You can either put it on the first carbon from the left or the first carbon from the right. Either way, it's the first carbon. I'm just going to put it on the first carbon from the right. So there's our double bond oxygen, single bond H. And let's fill in the remaining bonds. So remember, each carbon atom needs to have 4 bonds around it. And then we fill in our hydrogens. So this is what pentanol should look like. If you had the mirrored compound, meaning this compound just reflected where your oxygen is now on the first carbon from the left, that's perfectly fine. 2.6 says, using molecular formula, write down the balanced equation for the complete combustion of compound A. Let's have a look at compound A. That was C9H18. So C9H18. Now the good thing about combustion reactions is that they are completely straightforward in the sense that it always reacts with oxygen gas. Okay, so it burns in oxygen, that's combustion. And your products are always CO2 plus H2O. The only tricky part here is that you have to balance this on your own. So remember in grade 10 chemistry, you were first introduced to balancing chemical equations. So yeah, that comes back here. Now to balance this, let's first work with the carbon. So we've got 9 carbon on the left and only 1 on the right. Let's put a 9 in front. Then let's look at hydrogen. We have 18 hydrogen on the left and 2 on the right hand side. We can balance that by putting a 9 in front of H2O. So the last thing you balance is the oxygen. On the left hand side, you have 2 oxygen. On the right hand side, you've got 9 times 2, which is 18. Plus another 9, you have 27 oxygen. Now, here's what happens when it comes to having an odd number. Because remember, you have 2 on the left, but there's no way you can balance out 27. There's no way you can balance that out because you have 2 on the left-hand side. So they're not even numbers where it's easy for you to just put a value in front. Instead, you're going to ask yourself, 27 divided by 2 gives you what? That is going to be 13.5. So in front of my O2, I'm going to place 13.5. And sometimes, some teachers or some learners, when they do this, they don't like working with decimals. So instead, they'll say 27 over 2 instead of the 13.5. That's the same thing, the equivalent. So I'm just going to work with 13.5. And here's the thing. When you are balancing chemical equations, you can only use whole numbers as your coefficients. So we don't want decimal numbers. If ever you get a 0.5 like this, your next step is multiply your entire equation by 2. So we multiply throughout by 2. So let's do that. Multiplying everything by 2, your first reactant gets a 2 in front. Now we have 13.5 times 2, which is going to be 27. On the right hand side, we have 9 times 2, which is 18. And again, 9 times 2, which is 18. Now let's check if this is balanced. So on the left hand side, we've got 2 times 9, we have 18 carbon. On the right hand side, we have 18 carbon. On the left, we've got 2 times 18, which is 36 hydrogen. On the right, we have 18 times 2, which is 36 hydrogen as well. On the left-hand side, you've got 27 times 2, which is 54 oxygen. On the right-hand side, you have 18 times 2, which is 36, plus another 18, which gets you to 54. So this equation is now balanced. So just remember that if you get a 0.5, you cannot leave decimal coefficients. You multiply the entire equation by 2. Please remember to like, subscribe, and turn on your notifications for more content.